In this video, we'll be going over a little bit more about our friend regression. So, instead of using only one predictor in a regression model, we can do a regression with multiple different predictors. So, just as in the bivariate case, we're going to conduct a hypothesis test to see whether our regression parameters differ from zero. In other words, what are the chances that we would observe this value of B predicted if the actual value of beta were zero? So the standard error of our beta predicted value, in the multivariate case, we need to compute that standard error as follows with this formula. Now, I'm not going to make you memorize this or do any of this by hand, and this is purely just for your knowledge so that you can see how all of this works. But the formula accounts for the correlation between x1 and x2. And if we didn't do this, we would artificially inflate the amount of independent variation in x1. Sometimes, we want to be able to interpret the effect of a 1 unit change in x in terms of a percentage change in y. So maybe how much additional income do I get from one more year of education? $4,000 might be meaningful, but that depends on what the average earnings are. And maybe an estimate like an 8% increase in income would be more interpretable. And this is usually how we model crime, for example, at a city level. So if we have a logged dependent variable, for example, we just take our derivatives, we take our model here, and we find that a 1 unit change in x1 is associated with a change in y of beta 1. Or we take our model and we find a 1 unit change in x is associated with a change in y of beta 1 over y. And this is all just to show you guys the mechanics of how all of this works, and we'll be performing these in an applied way in Excel and in R. But first, as an example, take our model here, where y is income and x1 is education. Our beta 1 value is about $4,000, and this indicates that one more year of education leads to a $4,000 increase in income. Now, if we take the model here, one more year of education leads to a $4,000 increase in income with the same. Now, let's say we want to evaluate this if our income is $50,000. If our beta 1 is $4,000 divided by $50,000, we end up with a value of 0.08, or 8%. This regression evaluates at the average value of y. So note that the ln function approximately estimates the percentage change, but these may not always be completely exact. And we know that because in regression and in statistics in general, there's always some kind of value of error, because if we could all predict things completely perfectly, well, we'd probably all be rich. So let's move on to R and Excel and do some of this in some applied examples.